Okay. Good morning, everybody. Can you see my iPad? Yes, I can't see I don't know why, but I can't see the iPad on the screen. Okay, so let me remind you where we were last time. So I defined a geometric characteristic of lattices, which is the Minkowski successive minima, which measures the lengths of the shortest vector, the next shortest vector, and so on. And then at the end of the lecture, I defined another similar looking geometric invariant, which requires some technical background. So let me recall what that is. So L is a lattice in Rn. L0 in L is an additive subgroup. But it's not necessarily a lattice. So it's the span over Z of R linearly independent vectors in L. And so this means it's a additive subgroup, and it's the number R is called the rank. And with such an object, we associate a number. First of all, let me remind you what it means for this to be primitive. L0 is primitive. This is all things we've already seen, recall. L0 is called primitive if there exists vi plus 1 up to vr plus 1 up to vn such that u1 vr plus 1 up to vn is a basis of L. So this is, so you can complete the generators of L0 to a basis of L, and we proved in lecture 1 that this happens if and only if the intersection of L with the span over R of L0 is L0. So it doesn't depend, in this definition, it seems to depend on the choice of the UIs, but with this criterion you see that it doesn't depend on the choice of UIs. It's purely a property of L0, and then we say that L0 is primitive. And associated with such an L0, we can define a co-volume, and we can define the ith, alpha I of L to be the nth of the co-volume of L0 for all additive subgroups of rank I. And there's this notion of a co-volume of a additive subgroup is something that I want to spend time on because it's not a lattice. We define the co-volume of a lattice to be the n-dimensional volume of a fundamental domain. But this object doesn't have a finite volume fundamental domain. And what we mean by when we say the co-volume is we mean an I-dimensional, we mean the co-volume of L0 in an I-dimensional subspace, which it spans over R. So let me also say that this number can be thought of slightly differently as follows. I can add another condition, namely that this additive subgroup is primitive, and that won't change the infimum. So this is another definition of alpha I of L. So this is something we'll see in a moment. It's easy to see that it doesn't affect the infimum if you make this additional requirement. And also, it's actually a minimum. It's this infimum is actually achieved, and this so this is something we'll see today, and this is something that we'll see later in the course. That this infimum is actually a minimum. Okay, so this is the notion of alpha I, and like I said, I need to make sense of this quantity, and so let's remind ourselves. So making sense. I'll explain what the issue is here. So L0 is a lattice in the span over R of L0, which is isomorphic as a vector space to R to the R, where R is the rank of L0. And so the co-volume of L0 is the volume, R-dimensional volume, of a fundamental domain for L0. So far, this seems like a reasonable definition, but it's actually, there's something tricky going on here, which is that we need to understand what we mean by this volume. So typically when we work with the notation that I'm using when I say volume is the Lebesgue measure. When we work with the Lebesgue measure, we understand it in the following way. Recall, what is Lebesgue measure? Lebesgue measure on R to the, let's say, K, which we denote by vol, is the unique Borel measure on RK. So it's defined on Borel sets in RK, which is translation invariant. And this means that the measure of A is equal to the measure of A plus X for any a Borel set and any X in RK. So the measure of a set doesn't change when you translate it by a vector and is normalized. And this means that the measure of the unit cube is 1. That's the normalization of the measure. So this makes sense on RK. The last condition here makes sense on RK because on RK we have our coordinate axes and we know what we mean by this cube, this unit cube. But what we're talking about right now is the volume of a unit cube on this space. And this space is abstractly isomorphic to an R-dimensional vector space, but there's no preferred isomorphism. So it's not clear what we mean by this condition. So so let me just tell you how we normalize this, how we express this. So again, I'll explain the issue. So here is R is V, which is what I want to call the span of L0. And it's isomorphic to R to the R as a vector space. So that means that there's a linear isomorphism, let's call it phi, from R to the R to V, but there could be another linear isomorphism, C. There are many possible linear isomorphisms, and they differ by this map, which is the composition of what? Of C inverse with phi. And you might use this map to take a cube here, push it over here, and call that a unit cube, or you might take this map, and they differ by this transition function. The transition function, there's no reason why it should map a cube to a cube. It's just a linear transformation. So I'm also recalling a property of Lebesgue measure, which is that volumes change by the Jacobian. So if T from R to the K to R to the K is a linear transformation, then for all A and R to the K, Borel, the measure, the volume of T of A equals the absolute value of the determinant of T times the volume of A. And this is the Jacobian. And so this formula, this is the Jacobian of T. So when you just choose any linear transformation, we don't know that the Jacobian of this mapping is 1. So we don't know that we can use a particular coordinate system to define the normalization of Lebesgue measure. Okay. And so what are we going to do? We're going to use the inner product that we have on our space. Is there a question? We're going to use the inner product that we have in our space to normalize the measure. So solution. So define the volume on V to be volume of set A is C times, I'll explain my notation in a moment. So going back to this diagram, there's a volume here, which is Lebesgue measure over here, and we're trying to define the volume over here, or the Lebesgue measure over here. So let me call the volume over here vol sub v, and let me call this vol sub r to the r. And so we take a set here, we pull it back under phi, we measure it here, and we multiply by scalar c. So that's what this formula says. But c is not just any scalar, we choose it where c is chosen. So that if we have chosen an orthonormal basis in V, then when we pull it back, sorry. So that the set unit cube with respect to this orthonormal basis sitting inside V will be given volume 1. And now you can check that with this condition, no matter which, whether you choose phi or whether you choose psi, there's a distinguished collection of sets here. These collections are the unit cubes with respect to orthonormal bases, so they depend on a choice of some orthonormal basis. And you can check that whether you use this map or this map, the normalization by this scalar factor c will make this volume uniquely defined. Okay, so this is the unique scaling of the volume that we need to have in order to define the volume element on V. We're using the inner product. Okay, so again, I should also mention that this does not depend. This does not depend on the choice of the orthonormal basis. If we were to choose two different orthonormal bases in V and compare the Jacobian, and we use this normalization, we'll see that we're going to get the same normalization in both cases. Okay, so this is the definition that we're giving to the notion of covolume. So use vol V to define covolume of L0 as vol V of a fundamental domain for L0. In V, for instance, you could take the you could take the cube, the parallelohedron given by the basis for L0. So a sum AI UI AI01 I'm sorry. Okay, so this is the definition of the volume. And now let's check that I said earlier that in this definition of the alpha i's, we can define in two ways. We can just take the infimum over all additive groups, or we can add another requirement that they're primitive without affecting this this definition. And why is that? Well, obviously, if you add in the requirement that you're primitive, you're taking an infimum over a smaller set because you're adding a condition. So this number up here is a priori smaller than this number over here. But at the same time, if we had a non-primitive, if L0 is not primitive, then we can define L1 to be the intersection of L with the span of L0. So this is a primitive this is a primitive additive subgroup that contains L0 with some index, and then as we saw, the co-volume of L0 will be the co-volume of L1 multiplied by the index of L0 inside L1 as an additive subgroup. So in particular, the co-volume of L1 is smaller than the co-volume of L0. So every L0, primitive or not primitive, contains a primitive additive subgroup of smaller co-volume. And so this does not affect, so the infimum won't change if we restrict ourselves um, to primitive additive subgroups. So this explains why the infimum, let me just write it this way. Same set, but with the added restriction of primitive in definition of why we have equality in these two possible definitions. Okay, so this is the notion of these alpha i's, and these alpha i's are giving us a geometric quantity associated with any lattice. So there's an alpha I in every dimension I between 0 and n, the volume of the dimension of the lattice. There's a convention, what happens in 0 dimension. In 0 dimension, you just, the co-volume of the trivial subgroup is by convention 1. It's the only subgroup of rank 0, and the alpha 0 of L is 1 for any lattice. So, okay, that's just a convention that will be useful for making formulas more precise. So as a first approximation, I'm going to this proposition will tell you that this geometric quantity can be recovered from the lambda i's, from the Minkowski successive minima that we already discussed. So let me write that down. So for each dimension n, there exists a constant c bigger than 1, such that for any lattice, L, and for any I, um, the quantity alpha I of L, which we care about, is bounded above and below by the product of the first L successive minima. So let me draw a picture just so you get used to this. So if you think about, well, it's hard to draw a picture, but let me try to give an example maybe. So let's take n to be 3. Let's take L to be, I don't know, 1/2 z e1 z e2 plus 2z e3. Okay? And so it's easy to check that in this example, this number is lambda 1 is 1/2, lambda 2 is 1, lambda 3 is 2. This is the shortest vector. This is the next shortest vector that's linearly independent of it. And 2 times e3 is the next shortest vector that's linearly independent of the first two. And in this example, it's also easy to check if we, first of all, lambda 1 is always equal to alpha 1. I should have said that earlier. Alpha 1, this co-volume is just the shortest possible length of a vector in V, which is a definition of lambda 1. I see a question in the chat. Is there a question?
Lost you for a minute there.
Ah, okay. Can you hear me now?
Yes.
Okay. So let's talk about alpha 2 for a moment. So alpha 2 is the smallest co-volume of a lattice. And in this case, alpha 2 will be the co-volume of the lattice generated by the first two of these vectors. This one, the shortest vector, and the next shortest vector. And if you think about it, you're not going to be able to find any other lattice, sublattice in L, which has a smaller co-volume. And then the co-volume here is exactly 1/2, which is the product of lambda 1 and lambda 2. So in this particular example, we have equality lambda 1 equals lambda 2 equals alpha 2, lambda 1 equals alpha 1. And then clearly, co-volume of L, in this example, this is the co-volume of L, and the co-volume of L is clearly alpha 3. The top dimensional alpha n is exactly the co-volume. Okay, so that's the, in the proposition, in the example that I'm giving, we have precise equality of alpha I in this product, and the proposition says that these two quantities are the same up to constants that depend on dimension, but I'm not specifying. I'm not telling you what the constants are, but I'm just saying that they exist. So proof, I'm going to give the idea. This is an exercise. So exercise, we will prove for n equals 2 or 3 to give the idea. Let's introduce a notation. So let's write A less B if A and B are functions of a lattice L, and there exists a constant C depending on n, but independent of L, such that for all L, we have this inequality. So this is a standard notation, roughly less than or equal to, and then also let's write a this. Okay, let's prove case n equals 2. Alpha 1 equals lambda 1. This is, as I said, by the definition of alpha 1. They just have the same definition. Alpha 2 equals the co-volume of L. Again, this is by definition of alpha 2. You're taking an infimum over a set that only contains one number, which is co-volume of L. And the co-volume of L is equal to lambda 1, lambda 2, up to these constants by, this is by Minkowski's second theorem. We saw in Minkowski's second theorem that this product is, if you take up to the dimension, up to constants depending on the dimension, is equal to the co-volume. So that's the case n equals 2. It's just a corollary of Minkowski's second theorem. Let's do the case n equals 3. So again, alpha 1 is equal to lambda 1, alpha 3, which is the co-volume of L, is essentially up to constants equal to the product. And so we care about I equals 2 in this case. So let's establish this in two inequalities. So let's take V1, V2 in L linearly independent, realizing the Minkowski successive minima for this lattice L. Let's call those V1, V2, and let's let L0 be the span over Z of V1 and V2. So L0 is some additive subgroup of rank 2 in L. And so alpha 2 of L is less than the co-volume of L0. This is by definition of alpha 2. The co-volume of L0 is the volume, two-dimensional volume of the following set, a parallelepiped spanned by V1 and V2. This just goes from 1 to 2. And in 2 dimensions, this is a parallelogram. In 2 dimensions, the area of a parallelogram is the lengths of the sides times the sine of the angle. So theta is the angle at the base of this parallelogram. And this is less than V1 times V2, which is lambda 1 times lambda 2. So we got one inequality. So alpha 2 is less than lambda 1, lambda 2. Let's go in the other direction. Suppose that L0 is the span of 2 vectors U1 and U2, and L0 realizes the infimum or almost realizes the infimum. For this proof, I don't really care about whether it realizes the infimum or almost realizes the infimum. Once we know the infimum is a minimum, we can just take it to be the co-volume of some L0, but for now we don't know that. So let's just say that alpha 2 of L is, let's see, bigger than 1/2 the co-volume of L0. So again, alpha 2 of L is the infimum of such co-volumes. And it's actually, as I said, but I didn't prove, it's actually the minimum of such co-volumes. If it were the minimum, if you already knew that it was the minimum, you could just take L0 to realize the minimum, and then you would have equality here, but we care about things up to constants. And so this, I'm taking L0, which realizes the infimum up to some constant, maybe up to this factor of 1/2, okay? And so now the co-volume of L0, I'll write this down first and then explain. So it's the product of the successive minima of L0 up to constants, and this is because of the case n equals 2, which we did before. So this is kind of like an argument by induction. You already know that this is the second, this is the alpha 2 of L0, and this is the product of lambda 1 and lambda 2 of L0. In other words, the shortest vector in L0 and the shortest vector in L0, which is independent of the first. And since the definition of the Minkowski second minima, the lambda i's can only go down if we take a bigger lattice, because this is the shortest non-zero vector in L0. L0 is the sub-lattice of L, a subgroup of L, and this is the shortest non-zero vector of L. So obviously, if we replace this by this, we decrease, and similarly, if we replace this by this, we also decrease. And so in total, we get that, that alpha 2 is bigger than lambda 1, lambda 2, which gives the other direction of this inequality. So basically what you're seeing, in fact, is that this this comparison, this proposition, basically follows from an induction. Where did it go? This proposition here basically follows from some kind of an induction and from Minkowski's second theorem, which we already did. Now, we only did Minkowski's second theorem for the Euclidean norm, but we're working with the Euclidean norm here. In any case, we're not really worried about precise constants. Today, we're only trying to establish that there are constants depending on n. And so this is working fine for us. But of course, it's very interesting to actually know these numbers precisely. And this kind of a very rough bound is not very useful for many, many applications. So the whole point of this discussion that we're having now is that these lambda i's give us some information about, some geometric information about the lattices, these lambda i's. And so do these alpha i's. And as a first approximation, alpha I is the product of the lambda i's, but it's not really exactly the product. And in some cases, this is a much better information, and in some cases, this is a better information about what's truly going on with the geometry of the lattice.
Is a typical lattice, does a typical lattice behave like the example you gave? Is it kind of closer to the...
So what we're going to see, which is somehow very hard to visualize, we're going to spend a lot of time talking about the typical lattice. The typical lattice has all these lambda i's very, very close to each other. I gave some examples with the Leach lattice and the E8 lattice, and I said some things, and we're going to see that that's quite common. So this is a bad example in a sense. This vector is much shorter than this vector somehow. And so all the lambda i's are roughly close to each other, and they're roughly of length. If the co-volume of the lattice is 1, and you think of Zn as your example, then you might think the natural normalization, especially based on the fact that the product of the lambda i's is essentially the co-volume, you might think that the length should be close to 1. The length of the lambda i's for a typical lattice should be close to 1. But actually, it's much longer. So typically, it's of order square root of n in the dimension. Okay, we're gonna do a lot of discussion of that. And I think at the moment it's somewhat counterintuitive, but that's the geometry of a general lattice. You should think of lots and lots of vectors of approximately the same length generating the lattice, and they're all rather long. And in that sort of regime, there might be a very large difference between this number and this product. Any more questions about that? Okay. So what we're going to do now is we need a technique for computing these alpha i's, these co-volumes. And we're going to spend, this is going to be a bit of a fairly long technical discussion about computing these volumes. And this is goes by different names. So this is exterior algebra or Grassmannians or Plucker coordinates. So let me call that. So we will need some algebraic preliminaries. In order to compute these co-volumes. And for this, we will use we will discuss Grassmannians, or I'll just put up some keywords here. So, as you probably all know by now, in mathematics, there's a lot of things that are very, very simple once you understand them, but they're given kind of fancy names, and they look kind of scary at first. So this is one of those things. There's some algebraic techniques associated with computing volumes in Rn, of objects which are k-dimensional, where k is some dimension between 1 and n, and this goes under different names. And if you've taken a course in analysis on manifolds or integration on manifolds, you may have seen this. If you're taking in differential geometry, we sometimes show this, but often it sort of slips between the cracks and people don't really have a firm understanding of this. So I'm going to spend probably most of the rest of the lecture today explaining some basic algebra associated with computing volumes, and this goes under these names, okay? And this is a theory from the first half of the 19th century. And I'm going to do it very abstractly, very algebraically. So let's take the standard basis of Rn. And denote the standard inner product on Rn with these pointy parentheses. And for some parameter p between 1 and n, and a multi-index sigma, so sigma is the following information. It's an increasing collection of dimensions or numbers between 1 and n, consisting of length p, okay? We're going to define a formal expression, E sigma, in this way. So this is for now, this is just a formal expression. It's just a notation. Something we do with a p-tuple of standard basis vectors, that's all. So let's let the collection C and P be the collection of such expressions. It's a finite collection depending on the choices that we made over here. And clearly there are P places to put these indexes between 1 and n. So the size of C and P is n choose P. And let's let R and P denote, let's call this number, say L. Let's let R and P denote the L-dimensional real vector space spanned by the E sigma. So I'm thinking of the E sigma right now, again, as these are just formal symbols. And now I think of each one of these as vectors. And I just span a vector space over these vectors. I just talk about formal linear combinations over R of these vector spaces. And as a convention, if P is 0, I just denote R by Rn0. And so the elements in this vector space are called P vectors. And note also that if P is 1, we just recover the space Rn that we started with, because we're taking the formal linear combinations of the standard basis vectors, right? If P is 1, then the E sigmas are we just recover these guys and we get Rn back. And let's define an inner product I'm sorry, before we do that, let's denote by G sub n the direct sum as vector spaces of these RNPs. So the dimension of G sub n is the sum of P n over P, n choose P, which is 2 to the n. So we have a 2 to the n dimensional vector space, which we call G to the n. And on it, we put a inner product it's the inner product that makes these formal symbols orthonormal. Okay, so whenever you have a basis of a vector space, you can define an inner product by just defining the value that the inner product takes on your basis elements, and so that's our definition of the inner product. It's forced to make the vectors orthonormal, and you see that it coincides with the inner product that we already have if we restrict it to Rn1, to this to the initial subspace where the of one vectors, it's just the original inner product that we have, because the EIs were orthonormal with respect to the standard inner product. And if we, so when discussing, we're going to also allow formal expressions in the standard basis elements, but with a different order. So we can have J indices, J1 up to JP, J1 up to JP between 1 and n, and they will be interpreted as follows. If we see such a formal expression, and if one of the indices repeats itself, then we just think of this as signifying 0, the 0 element of the vector space. So if J, I'm running out of letters. So if JK is equal to JL for some K not equal to L, then this expression is just another complicated way for me of writing 0. And if not, so if the collection J1 up to JP is the same as the collection I1 up to IP, where the I1 up to AP are ordered as before, and JL equals I of pi L, so they're just a permutation. Of these P indices. So if that's the case, if there's no repetition, and these are the names, then we think of this formal expression as being either plus or minus the expression that we had before, depending on whether pi is even or odd. Okay, so this is a complicated way of saying the following thing. If you see this kind of formal expression, you can simplify it by, I'll just maybe change color just to explain things. You can just simplify these expressions. Whenever you see, I don't know, something like this, where the indices are in the wrong order, you just flip the order, and change the sign. Okay, and you can continue performing these kinds of operations so that whenever you have an expression of this type, you can change it into an expression of this type by some number of transpositions, and the sign will change some number of times. The number of times is the parity of the permutation. And of course,
is this? Oh, sorry.
Yeah, go ahead.
This is like, for now, you've sort of shown exterior product rules, right? From like
yeah. I'm defining the
geometry.
exterior. This is exactly the exterior power rules. I'm
Okay.
defining the exterior algebra from scratch.
Okay.
I'm just defining it as a formal object right now, and I'm going to make the connection to these co-volumes in a few seconds. Okay, so so that's the space. That's a space as a vector space with an inner product. So on Gn on the, this is called the Gn is called the Grassmannian. I should have said that earlier. Did I say that? This is the Grassmannian. The Grassmannian algebra. You'll see why it's called the Grassmannian, why it's called an algebra in a second. But this right now it's a vector space with an inner product. On Gn we have the structure of a real vector space with an inner product. And we're going to define a third structure, which is the wedge product. So we define a product rule. So this is denoted by this wedge thing. So this is an operation taking pairs of elements in the Grassmann algebra and forming a new one. So this is just notation. We take two formal objects in this algebra, and we map them to a new thing, which is denoted by U wedge V. And this is defined as follows. Firstly, one wedged with one, I should have said maybe earlier, one is a formal element of Gn. It's the generator, it's the generator of Rn0. So I should say it over here. By convention, this is this, and it's the span of there's a formal element which you could call 1, or you could call it E sigma, where sigma is empty. It has length 0, and we're just denoting it by 1, and it lives in Rn0. So 1 wedged with itself gives 1. 1 wedged with anything else doesn't change it. So 1 is like an identity for this multiplication rule that I'm defining. Well, sorry, let's define this on the basis only. So I define the product of 1 with any basis element by this rule. And then now I need to define the product on these E sigmas, and I define it as follows: EI1, EIP, wedge E, J1, E, JQ is just defined to be what you think it is. Okay? So I told you a few seconds ago how I want to interpret an expression like this where the indices are not necessarily ordered in increasing order. Sometimes it's 0 if there's repetition, and otherwise you can change the order and get some other expression. So you're seeing that I'm using this notation in order to define the product. And note that the multiplication rule takes two elements. One of them is a p vector and another is a q vector, and it either produces 0 or it produces a p plus q vector. Okay, so this is some kind of a product, and now you can extend it by linearity. So what I mean by that is if I take two vectors this is the general shape of a vector in Gn, and if I want to define the product between them, then this is a and the value of the exterior power operation on these pairs, and this is just the obvious extension by linearity to the entire space Gn. And let me just say one more word, and then we'll take a break. So now with this extra structure Gn, with this structure, Gn is what's called a unital associative algebra. So a unital, what is a unital associative algebra? So this is V is a unital associative algebra. If V is a vector space equal to the product which is associative, and multilinear. I'll say what this word means in a second. And contains a unit. A unit is a neutral element for multiplication, a 1. And multilinear, let me write that over here. Multilinear means this. Okay, so here I'm writing the product rule with this little dot just to signify that this is part of a general theory, but in our setup, this little dot is not denoted by little dot, it's denoted by this wedge object. And all I'm saying right now is that with this definition of the wedge, it satisfies these properties that you see here. Okay, it's associative, it's multilinear, and it satisfies. So it satisfies these properties and it contains a unit. Okay, so we've made the Grassmannian, which is a formal vector space, into this associative associative unital algebra. And why we do that, I'll leave you in suspense. Let's take 10 minutes, and after the break, I'll explain how this is related to volumes. So let's take 10 minutes. יש פה מישהו שהוא לא במיוט, לא יודע אם הוא רוצה שנשמע.
לא ממש.
Manuel, can you hear me?
Thanks. Perfect.
Okay, let's resume. So sitting inside these vector spaces are some special vectors. So these are, so if you have a p tuple in Rn, which we were thinking of as the Rn1, the first piece of this Grassmannian of degree 1 vectors, then if we take their exterior power, this is an element of, this is a p-vector, but it's this very special kind of p-vector, and it's called decomposable. Sometimes, or sometimes it's called a p-blade. I think I think decomposable is kind of confusing, to me at least. Blade, but I think it's more commonly used than p-blade. So let's think about this definition for a moment. So we had this structure of a product, and we have this kind of a product structure, and we have, where's our definition of it? This is our definition of the Grassmann algebra. And so the product structure is taking elements in lower dimensions, so lower p vectors. If you wedge a p vector and a q vector, you get a p plus q vector, or you get 0. And so it's always sort of pushing you up. And you can start with p elements of Rn1 and wedge them. You take p elements in Rn1 and wedge them, you get an element which is a p vector. But let me sort of convince you that you shouldn't expect to get all p vectors in this way. In fact, you get a very small minority of p vectors in this way. And that's simply, the heuristic here is just simply a dimension count. And so how many free parameters do we have when we're choosing this p vector? Well, we have n degrees of freedom for each xi because it's a vector in Rn. And so we have n to the p degrees of freedom for, n times p degrees of freedom for this, possible degrees of freedom in choosing this this decomposable element in the, which is a p vector. But if you think about the dimension of this space, it's much, much larger. It's n choose p. Okay, so a vast majority of the elements of this vector space are not of this particular form. But these are the elements which are important. Somehow, the way to think about it is the following. You have a vector space. Inside the vector space, you have these elements, which typically are the elements that you do care about more than the others. They are the ones related to subspaces. You care about your dimensional event called M. I'm going to take xi, and I'm going to write xi as a linear combination of the standard basis vectors. Oops. Okay, theCij's are real numbers. And so, for example, xi is column vector that looks like this. And now if I want to compute the corresponding p-blade, let's call this identity star because we're going to use it, x1 wedge dot 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 wedge xp will be sum over sigma c sigma e sigma, where the coefficient c sigma is the determinant of Cij's, with I going from 1 to p and j in sigma. Okay, so the determinants from now on, determinants are going to play a very prominent role in what follows. So this is a p by p matrix. We have the p indices of the vectors xi, and we have the p indices in the, maybe I should make this clearer. I'm only taking multi-indices that correspond to p vectors, and these are the indices that appear in the multivector. And so I get this kind of p by p determinant expression for the coefficients of these vectors. See a question? So if people want to ask, I see chat is popping up, but I'm not seeing what's on it. Okay. So if people want to ask questions, if it's not about technical problems, just unmute yourself. So let's just do an example so you understand what this is about. Suppose we're doing a four-dimensional case and a two-vector in a four-dimensional space. And so suppose we want to compute the wedge of these two four vectors. I'm going to compute their wedge. So first of all, in what dimensional space does this live? This is a 4-choose 2-dimensional space. So this is going to live in a 6-dimensional space. And I'll just write down the first few terms and you'll understand. So this is, oops, sorry. I'll write down a few terms. I'll write down like a generic term in this expansion, maybe the 2, 3 term. So the coefficient here is 2, 3. We take the 2, 3 minor. So maybe color. I should take the second row and the third row of both of these vectors and take the 2 by 2 determinant that I see there. So this is going to be C1, 2 times C2, 3 minus C1, 3, C2, 2, multiplying E2, 3, etc. Last expression corresponds to say E3, 4. So here we'll have a C1, 3, C2, 4 minus C1, 4, C2, 3. Okay, so this is what the formula is saying. Is this clear? This is how you compute. This is sometimes called working with the Plucher. This is this fancy word, Plucher coordinates. The Plucher coordinates you get by doing these determinants of all minors to get the coefficients of the product. So let's prove this formula. This is just a formal computation. So I claim, we have this formula star, and I want to understand what happens when you take a p-tuple and do a linear operation on the ith term in the p-tuple. Okay? So by definition, if we had, so this is a multilinear expression. And so for example, if I replace xi by alpha y plus beta z, then this expression is going to be replaced by alpha times x1 wedge dot 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 y dot 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 wedge p plus beta times x1 dot 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 wedge dot 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 z wedge dot 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 wedge. Ken.
Yeah. The screen is like paused, and B, the Plucher coordinates are the determinants, right?
The Plucher coordinates are the determinants of all these minors.
Yeah, and we can't see where you were writing. Like the screen is kind of stuck.
Is it completely stuck now?
Oh, no, now we see it. Thanks.
Now it's moving. Okay, I guess were you able to see this example, this worked out example?
Yeah.
Okay.
Just not the proof and the.
So I'm beginning the proof, and I just made a remark. I don't know. Yes, please stop me whenever this happens again. So I'm giving the proof, and I made a remark. I want to look at both sides of this expression, and I want to claim that both of these are multilinear in the xi's. Okay, so what happens if I replace, for example, x1 by alpha y plus beta z, where alpha and beta are scalars, y and z are vectors. Let me write it in color, maybe over here. And then I'll erase it. So if we do alpha y plus beta z wedge x2 wedge xp, this is alpha y wedge x2 wedge xp plus beta z wedge x2 wedge xp. Okay, this formula was part of the way we constructed these formal expressions. The product, we forced the product to be multilinear. It's part of the definition of being associative algebra. The same would be true, it's just more complicated to write, if we do this kind of linear combination for any xi, any index I between 1 and p. So that's what happens on the left-hand side. Now, what's happening if you do that on the right-hand side? If you do that on the right-hand side, you're changing this determinant in one row, in the ith row. And the determinant is also a multilinear expression. So both of these, both the left-hand side and the right-hand side of this expression transform in exactly the same way when we perform such linear combinations in each row of in each of the xi's. So now I'm going to erase this red stuff and just summarize what I said in one sentence. Proof: both sides of star transform identically if we perform linear operations on the xi for each individual I. So for that reason, it suffices to prove star, so we can apply these linear operations until we bring star to the case where it's composed of standard basis vectors. So it suffices to check star when the xi are eji for some ji. And again, both sides transform in the same way in permuting the xi. So we can assume that J1 is less than, etc., less than JP. So we reduce ourselves to exactly this case. And now we have to distinguish, or maybe I should put a less than or equal here. We can always permute things until we land in this kind of a situation. And now there are several cases. So if Ji equals Ji plus 1 for some I, so in other words, if there's repetition in this multi-index, if you have some repetition, then the left-hand side of star is 0. Where are we? This is, remember that this is star, and we decided that if you have some EI wedge EI, you get 0. And so this left-hand side becomes 0. And what happens to the right-hand side? So in these determinants, you have, for two different j's, you have the same vector in this sorry, for two different j's, you have the same vector. And so this determinant is always 0. Is what I just said correct? Yeah, so you have two rows here. If xji and xji plus 1 are the same, then the row I and the row I plus 1 in this matrix are exactly the same, and this becomes 0. So this works. The left-hand side is 0, and the right-hand side is also 0, because each matrix, each one of these matrices has 2 identical rows. What happens if we have strict inequalities? And sigma happens to be exactly then the left-hand side is exactly E sigma, where sigma is this multi-index. What about the right-hand side? Let's scroll up again to C star. Where is this? What about the, maybe I shouldn't have called this sigma. Let's call this guy sigma 0. Scroll up to the right-hand side. So on the right-hand side, we want, this is one of the multi-indices. This is one of the standard basis vectors in our Grassmannian. And this is some kind of linear combination of them. So we have to figure out all the different coefficients here. So first of all, if sigma is sigma 0, then this matrix just becomes, this matrix here just becomes the identity. And so the coefficient in front of E sigma 0 is 1. And if sigma is not equal to sigma 0, that means that at least one of the indices in sigma is not an index in sigma 0. So theCijs that appear here, we have one column which is 0, so the determinant vanishes. So let me write that down. So left-hand side is E sigma 0. Right-hand side, coefficient of E sigma 0 is the determinant of the P by P identity matrix, which is 1, and the coefficient of E sigma for sigma not equal to sigma 0 is the determinant of a matrix with a 0 column. Hence, so in both cases, in all cases, we have the left-hand side is equal to the right-hand side, and this completes the proof of the proposition. One more proposition. How does the norm, we define an inner product, so we have a norm. How does the norm behave with respect to this exterior power product? So it can't go up. So we have a kind of a submultiplicativity property. U wedge V norm is less than norm of U times norm of V, where this norm is the norm given by the inner product. This is an easy proof. So we take a vector in Gn. This is valid for all U and V in the Grassmannian algebra. We take two elements of the Grassmannian algebra, and let's write them in coordinates. Now what happens when we wedge two multi-indices sigma and sigma prime? Well, there are two cases. In the first case, if sigma and sigma prime have a non-trivial intersection, in other words, there's an index. So each sigma is a multi-index of some length. Sigma prime is a multi-index of some length. The numbers appearing in this multi-indices may intersect. So there may be a number which is, say, for example, 1 could be an element of this multi-index and also this multi-index, and then we say that the intersection is non-empty, and then this thing vanishes. Or if they don't vanish, then their union is another multi-index, and the outcome of this exterior power operation, by definition, is plus minus the corresponding vector given by their union. So once I know that, I can take the exterior power of these two elements and work with using multilinearity. And so this implies that the exterior power of U and V is the sum over all pairs sigma, sigma prime, which satisfy that their intersection is trivial, plus minus E, I'm sorry. Plus a inner product space, and you know how to express the. Ken, yeah.
I think we lost you again, at least I am. And
Yeah.
I also don't see the board moving. Oh, now it's moved.
There are like many lives frequently.
So the last thing that I saw is you writing the plus minus inside the summation.
Right here.
Yeah, right here.
Right here. Okay.
Yeah.
I'm not sure what to do about this, so we'll just take it slowly. So what I'm saying now is when you have a normed space, an inner product space, and you're trying to compute the norm, you're trying to compute the norm of a vector, and you have expressed the vector as a linear combination of elements of an orthonormal basis, then the norm is by the Pythagorean rule, it's the norm squared is the sum of squares of the coefficients. Are people hearing me now?
Yes.
Okay. So this means that the norm of U squared is the sum of the A sigma squared, sum over sigma. The norm of V squared is the sum of the B sigma prime squared. And the norm of U wedge V is the sum over all sigma and sigma prime with this extra condition that they don't intersect of plus minus A sigma B sigma prime squared, which is sum over sigma sigma prime disjoint A sigma squared B sigma prime squared, which is just okay. So all I'm saying is that here we have this extra condition that the two multi-indices are disjoint, and if we just relax that condition and we allow any pair of multi-indices, we get this expression, which is exactly the product of the norm squared of U and V. So I've established the inequality that I want. Okay.
If you have equality in this case.
Yeah, we're going to, let's write that as a question. We're going to talk about that soon. So what about equality? equality is not so easy to it's not so easy to give necessary and sufficient conditions for equality in the general case, but it is easy to give necessary and sufficient conditions for equality in the case of blades, in the case of decomposable elements. Okay, which we're going to get to soon. So this is a teaser. Let's get a corollary from this, which is settle a debt that I had in our previous lecture. So in the previous lecture, I mentioned something called the Hadamard inequality, which is a very simple fact. Let's see how it, let's remind ourselves what it is, and then just see how it follows from the formalism that we've already set up. So this is the Hadamard inequality. The determinant of a matrix is less than or equal to the product of the lengths of the columns of the matrix. So why is this true? I mean, this is an easy fact, but I'm just proving it, first of all, because I own the proof, and second of all, because we can sort of see how this all this machine that we're building, how it works. So we're interested, the left-hand side is the determinant of the matrix whose columns are the VIs. And so let's just multiply that by 1 for the moment. So this is the same expression multiplied by the norm of the multi-index, which contains, this is the unique element, the unique n vector, unit n vector. And so by product of norms, I can put this inside. And this n vector is E1 wedge, etc. En. And this is the determinant again of V1 up to Vn. And so now if you go back to the proposition, you see that this is exactly the expression for the wedge, the exterior product of the VIs. And then by our previous corollary, this is less than, by induction on the previous corollary, right? In the previous, so by induction in this proposition here, we have this. And so clearly by induction, we have that this is less or equal to this. So this is induction of previous proposition. And this fact is star. Let me just call that star. Star in the case P equals N has this particularly simple form. Okay. This is definitely not the easiest proof of the Hadamard inequality. Hadamard inequality is almost trivial, but just getting you used to to how you work with these expressions. Here's another, yeah.
Question? A question about the proof of a proposition.
Yeah.
Can you move it up?
This one here?
No, not the corollary, the proposition itself.
The star formula, yeah.
Yes. So you're writing that the wedge sum is this plus minus a sigma b sigma tag, but
wait. So you want this the proof of identity star here, or the proof?
No, the proof that the norm of u wedge v is at most the product of the norm of u and v.
Right.
Yes. So you write that u wedge v is the sum of plus minus a sigma b sigma tag, e, and the union of sigma and sigma tag. But couldn't two different things come, like you can write something as the union of sigma and sigma tag in a few different ways.
Right. So they will, this sum
Like I need to say that this is somehow an upper bound or something.
No, it won't somehow formally. I mean, you're saying it's correct, but I never said that this is sort of like, oh, I see. You're right. Did I say something wrong?
I think you need to say something like that this should be.
Okay, I need a Cauchy-Schwarz inequality in each
Yes.
expression. Okay, thank you very much for the comment. Good point. So let's put a red danger symbol here, and you're right. I'll make a correction. Yeah, there's a mistake in the proof. There's something.
What is a mistake? I didn't understand.
So I was saying that when you have a vector and you have its expression in an orthonormal basis, the norm of the vector, the norm squared of the vector is the sum of the squares of the coefficients, and that's correct. So in other words, the formula, now I'm stuck. This formula is correct. This formula is correct. Now, however, in this expression here, some of these elements appear twice or more than once. So sigma, you can get the same, let's say tau is sigma union sigma prime. You can get tau as sigma union sigma prime in several different ways. And so this sum is correct, but there's repetition. And so this is not really the coefficient in front of this term. You have to collect the coefficients.
Great, thank you.
And so, okay, thank you for the comment. So I'll be posting a correction. The statement is still correct. The proof is similar, but there's a little step that I forgot. Okay. Where was I? Okay, so here's another corollary. So when does this product vanish? It's not zero if and only if x1 up to xp are linearly independent. And I claim that this follows immediately from star. Let's just think about this for a moment. I won't write anything down, but let's think about this for a moment. Let's first prove the implication that if they are linearly dependent, then this is zero. So in other words, if this is not true, then this is not true. Okay, so if if this is not true, then this is not true. So if there's a linear relation between the xi's, then this product is zero. If there's a linear relation between the xi's, for example, suppose xp is a linear combination of the other xi's. Let's go back to star. If there's a linear relation between the xi's, then this matrix, the pth row of this matrix, is a linear combination of the other rows of the matrix for every choice of c. So all of the coefficients here vanish, and we get zero. On the other hand, if the ci's are linearly independent, then one of these minors, so if the ci's, maybe it's better to look at this over here. If the xi's are linearly independent, and we just write them as a p by n by p matrix by putting them alongside each other, then one of the minors has non-zero determinant. And if one of the minors has non-zero determinant, then one of the coefficients is non-zero, so the left-hand side does not vanish. So that's the proof. So I'm not writing anything down. You can check that it's immediate from start. This is kind of a complete, it's the usual thing in mathematics. It's a complete, when you're lying, you have to lie several times without blinking to make everyone convinced that you're telling the truth. So I'm lying, in some sense, I'm not giving you a proof, but I'm replacing it by three things. First of all, I'm saying that it's immediate. And to make it stronger, I'm giving it to you as an exercise to check that it's immediate. But it is simple to check using start. So let's have another proposition. How do you, so let's say that definition. Say that two non-zero p vectors are proportional. Two non-zero vectors in general in this grasping algebra are proportional if there's a scalar c such that v2 equals c v1. If this happens, then because they're non-zero, then c is necessarily non-zero, and then this is symmetric. This relation is symmetric in v1 and v2. Proposition. Suppose you have two p-tuples y1 and yp, x1 and yp, and they're both linearly independent p-tuples. We want to know when they're proportional, when the corresponding p-blades or decomposable elements are proportional. And this happens if and only if they span the same space over R. Okay? Proof of this fact. So let's first assume that the space generated by x1 to xp is the same as space generated by y1 to yp. So let's suppose that V is the name of this space. And let's it's also the sum of it's also the span of the yp's, so that then each yi is a linear combination of some of the xj's. And so yi is from j goes 1 to 2, ji xj's, and therefore y1 up to yp is, and each of these, in each one of these situations, we have linear combinations of xj's. And so now we can use multilinearity. We can, so I'll just manipulate using multilinearity. When you open when you open up this expression, two things may happen. Either some xj meets another xj with the same index, and then this quantity vanishes, or you just get all the xi's in some order, but then you can change the order using the rules for the alternating rule, and at the end of the day, you get a multiple of x1 up to x2. So this proves the first direction. For the second direction, for the second direction, we're talking about linearly independent p-tuples. And so by the previous proposition, this quantity is non-zero when these tuples are non-zero. So we know that the product of the yi's is non-zero. And so, so if we're assuming that the product, where are we? We're assuming, now we're assuming that, oops, I didn't even write this down clearly. I meant to say that these guys are proportional. So we're now assuming that x1 through xp, x1 wedge x up to xp and y1 wedge up to yp are proportional. And we already know from the previous corollary that they're non-zero. And so the proportionality constant is not zero. So y1 wedge, etc., yp is c x1 wedge, etc., xp with c not equal to 0. And so let's look at yi wedge x1 up to xp. This is the same as c inverse 1 over c y1 wedge yi, sorry, wedge y1 up to yp, right? x1 up to xp wedge is y1 up to y wedge with c moved over to the other side. So we get that this is this. But here we have repetition, so this becomes 0. So actually, I don't think we proved this formally, that we know that the EIs, if they meet each other, you get 0, but it follows from star. So this follows from star. If you have any repetition in a p vector, you get, if you wedge anything with itself, you get 0. Sorry. I'm sorry. And so this means, by the previous proposition, that yi x1 up to xp are linearly dependent, but x1 through xp are linearly independent. And this means that yi is in the span of the xj's. This is true for all I, and hence span yi is contained in the span of the xj's, and by dimension, they have the same dimension, we get that they're equal. Okay, any questions about this? Okay, so let's take 10 minutes and have some phone calls to answer, I guess. So let's take a 10 minutes break. Okay, let's continue. So let me go back to this statement again. So what you're seeing in this statement is that these exterior powers, these p exterior powers, if you take two different bases of the same p-dimensional space, which is the condition that you see over here, you get the same vector up to scaling. So what we can do now is say that the p-dimensional subspaces of Rn are being mapped into lines in this space Rnp. So this is something classical in algebraic geometry. It's called the Plucker embedding. So let me write that down. And so we, previous proposition, this is just, we don't need this, but this is just for your education. So previous proposition gives a map from something called the NP Grassmannian over the field R. So this is the p-dimensional linear subspaces of Rn, the collection of all of these p-dimensional linear subspaces, and this is mapping to the p vectors projectivized. So this means lines through the origin in the space Rnp, the space of p vectors. And the mapping is that the span of x1 up to xp is mapped to the line running through the p vector x1, wedge xp. So by the previous proposition, if we take two different expressions giving us a p-dimensional linear subspace spanning the same p-dimensional linear subspace, then this map is well defined. So it doesn't depend actually on the choice of the basis. That's exactly, that's one part of this statement. Where is this gone to? Right here. So if you have two different bases for the same linear space, you get two vectors which are proportional. And so that means that this map that I wrote down is well defined. And the converse saying that if they're linearly proportional, then the vector spaces are actually the same. That just means that this map is injective. So this is injective. So I'll just write it in this form. Oops. It's injective and well defined by the proposition. And this map is called the Plucker embedding. So that's a remark. And so what we're seeing is that these p vectors encode a little bit more information than just what space you're in. So this expression here determines the line through this expression, the formal line, and the formal line tells you the space the vectors span. But there's some additional information if we care about the length of this vector, and that's going to be the co-volume, and that's where we're headed now. Before that, there's another famous identity, which is we're going to be using. So let's call this a lemma. This is called the Laplace identity, and it's also a special case of something called the Cauchy-Binet formula. And it says the following thing. Suppose we have two p tuples, x1 to xp, y1 to yp, vectors in Rn. And we want to understand the inner product between the corresponding p vectors. Then this is expressed as a determinant of the matrix that you get by taking the inner product of the individual vectors. Okay, so again, this is the inner product on Rn, which we're assuming that we know, and this is the inner product on this Grassmannian algebra, which we also defined, and now we're getting a formula that connects these two things. And again, as usual, the determinant is popping up. So this always happens again and again. Proof, it's a similar kind of idea. We first check this for standard basis elements. First, check for the case that x1 wedge, etc., wedge xp is suppose sigma and tau are two multi-indices. X1 through xp is e sigma, y1 through yp is e tau. So let's check this expression here. The left-hand side, this becomes either 0 or 1, depending on whether sigma equals tau or not. And what about the right-hand side? Well, if the sigma equals tau, let's see, I guess what I wanted, sorry. I don't only want the xi's to be, this wedge to be, let me write this down. The case that I want to treat first check for x1 up to xp being ei1 up to eip, where sigma is this multi-index. Sorry. And again, y1 up to yp being ej1 up to ejp, where tau is this multi-index. Okay, so this is a very special case where the xi's and the yj's are standard basis vectors. And then this is true because if sigma equals tau, then left-hand side is 1, and the right-hand side is the determinant of the identity matrix, which is also 1. If sigma is not equal to tau, then for some I, xi is different from yj for all j. So in other words, one of the indices appearing here does not appear here, and therefore the right-hand side has a 0 row and a 0, and left-hand side is also 0. So in this case, the statement is true. And in the general case, as before, I'll leave it as an exercise, reduced to a special case by row operations, by taking linear combinations. So I'll leave that to you as an exercise. Both of the sides of this expression, here, transform in exactly the same way when you perform row operations on the xi's or on the yj's, and you can reduce to this case. So this is the proof or sketch of proof of the Laplace identity. And let's obtain some corollaries from this. First, let's answer the question that you've been waiting to hear the answer to, which is what happens if you have an equality in the norm of wedges inequality that we had before. So here's the corollary. So if you have U1 up to UK, V1 up to Vj, and suppose that they satisfy that U, or maybe choose a bad choice here, V1 up to VL, and suppose they satisfy that Ui and Vj are orthogonal to each other for every I and j. Then the exterior power that you get by multiplying all these guys, its norm is the product of the norms. And actually, this is if and only if. So we're for the case of products of decomposable elements. So this is a decomposable element, and this is a decomposable element. For products of decomposable elements, the norm inequality becomes an equality exactly when they're orthogonal. We're only going to need this direction, so I'm going to prove this direction. This is immediate from the class identity. So let's just compute this thing in terms of inner products. Oops. Squared. So Laplace identity says that this inner product is some kind of a determinant of, and I have to take each one of the individual guys here and multiply it by each one of the individual guys here and form a matrix. So in our case, we have K plus L elements. So this is going to be a K plus L times K plus L matrix, and it's going to look like this. There are going to be 4 blocks. This is of size K, this is of size L. Up here, we have the UIs meeting the UJs. Up here, we have the UIs meeting the VJ primes. Up here, we have the VIs, VI primes meeting the UJs. And here we have the VI primes meeting the VJ primes. And this is for I and J. Going from 1 to K, and I prime and J prime going from 1 to L. But these terms are 0 because we assumed that all the UIs are all orthogonal to all the VJs. And so this equals, so we get a block form, and so this equals the determinant of UI UJ times the determinant of VI VJ. And again, we apply the Laplace identity, and we get this. So taking square roots of both sides, gives you the identity that you want, gives you this identity. Okay, so this is a quick proof using the Laplace identity. And as I said, this corollary can be upgraded to an if and only if. In other words, if you, let me just say that in words, I'm not going to write it down because we're not going to use it. Suppose you know this condition that all the UKs are, I'm sorry, suppose you know that this is a, you're taking the, you have equality in the inequality that we had before, and this is a p vector, this is a k vector, and this is an L vector. In other words, these are both decomposable elements. Then you conclude this orthogonality. But we're not going to be using that, so I'm not telling you the proof. And let's draw another corollary, which is the main reason we're interested in these, all of this algebra. And finally, we're ready to state it. So corollary. So suppose we have lattices, a lattice L and an additive subgroup. So L is a lattice, L0, an additive subgroup of some rank P. Spanned by U1 up to UP. So these UIs are, these UIs are a basis for L0. Then the covolume of L0 in the sense that we gave before is the norm of the exterior power of the UPs. So this corollary explains why we're so interested in this, all of this algebra for computing these kinds of expression. And so let me just add a remark. So, so decomposable elements U1 up to UK carry two bits of information. The span over R of U1 to UK, which is encoded by the line through U1 in UK. This is the previous remark about the Cooper embedding. And the covolume of the span over Z in this span over R. And that's the norm. Okay.
Can you, can one decide if I give you a line in RPN?
Yeah.
Can you decide whether it comes from a decomposable vector from a subspace?
I don't think in any easy way. I mean, you can compute a lot of. I think you can try to solve some equations. I don't think there's an easy criteria.
Okay.
Maybe I'm wrong. I don't know for sure, but I think it's not an easy problem.
Okay.
But I'm reminding you of the previous thing I said. This is a very low dimension in the spaces. The space of p vectors typically has a much higher dimension than the ones which actually do represent subspaces. I think there was another comment.
Wouldn't it be just computing some ranks?
I don't think it's just ranks. So you're given the p vector as a linear combination of the standard basis elements.
So for p equals 2 it will be just computing a rank of a matrix, right?
I don't think so. I don't think so. You're given, so let's say we have this example of two vectors in R4. So you're given 6 numbers, which is you're given 6 determinants of 2 by 2 elements, and you have to sort of see whether these 6 determinants come from 4 columns. And yeah, so you have to solve this sort of same linear equation with the same coefficients.
For pure tensors, it's just computing ranks. I need to think about wedge products, but I think if you arrange it in a matrix, you can make it.
Okay, let's just leave it open. I'm not sure about the answer. I think it's a good exercise. I'm not sure about the answer. Okay, let's prove this corollary. So again, as usual, it's always the same kind of scheme of proof. We start with a simple case for which we know that the statement is true, and then we sort of generalize. So here, the simple case. Okay, what's the statement again? So here we have a lattice, an additive subgroup, and so there is no standard basis because we're not in a coordinate plane. These are not coordinate. These don't. This is a p-tuple. It's not spanned by EIs in general. So, but the standard notion here is the orthonormal case. If the UIs are orthonormal, then we know how to compute this, and we're also going to be easily able to compute this. And also the same is true if the UIs are orthogonal, but not orthogonal just means that pairwise orthogonal to each other, but not necessarily normalized to have length 1. So let's assume that, assume first the W1 up to WP are orthogonal and linearly independent, which means that WI, which one inner product WJ is 0 if I is not equal to J, and the norm of each WI is not 0. So now using the Laplace identity, oops. This becomes the determinant of a matrix, and this matrix is WI's WI's multiplied by WJ's, and this gives you, when you multiply these things out, all of them, all the off-diagonal terms are 0, and the diagonal terms are the product of the WI's, the product of the norms of the WI's squared. And so this is also the square of the volume of the corresponding box, right? This is this object inside the brackets is a box whose side lengths are given by the norms of these WI's. So if I square the product, then I get the square of the volume. This is with our notion of, if this is not here, this is the volume on V in the previous notation. V is the span of the WI's. Okay. So now now that we know this, let's talk about a general case. So the co-volume of L0 is the volume over in V of a similar set. Oops, this should have been a 1. But now this is a parallelepiped. It's not a box. It's not the sides are not orthogonal to each other. But what we're going to do is compute this by doing the Gram-Schmidt procedure. So apply Gram-Schmidt to the VIs to form an orthogonal collection W1 to WP. W1 is U1, W2 is U2 minus U2 W1, W1, etc. So you all know the Gram-Schmidt procedure. Gram-Schmidt is explained sometimes in two different ways. In one situation, you might be trying to construct an orthogonal collection, which is what I wrote over here. And what you do is at each step, you subtract from your vector the orthogonal projection onto the space of vectors that you already have. In another version of the Gram-Schmidt procedure, you want to make this an orthonormal collection, which means at each step you want to normalize the vectors, and I'm not normalizing the vectors. In the orthonormal case, W1 would be U1 divided by its norm, W2 would be this expression divided by its norm, where these guys would have a simpler expression because these would already be normalized. Okay, but this is the standard orthogonal, this is standard orthogonalization procedure. Okay, so then the covolume of L0, which we already said is the volume of this that we had before. It's also the volume of another set, which is the box generated by the WIs. And this isn't the same set anymore, but the volume is the same. The reason the volume is the same is one, the box is obtained from the parallelepiped by a linear transformation of determinant 1. And what is the linear transformation? You can already see it right here. So this is the linear transformation. W1 is U1, W2 is U2 minus something which only involves U1. So if you work out what this means in terms of a matrix, this is a triangular matrix with ones on the diagonal. So its determinant is 1. And so the Jacobian rule tells us that these two sets, which are different sets, have the same volume. And by what we already saw, this is, as we know, this is the product of the norms of the WPs. So we're getting the product of the norms of the WPs. And now let's check that's also what the exterior power of the UIs would give us. So the exterior power of U1 up to UP is, I'll just write it this way. We can invert this formula to express UP as WP plus this term, which is a linear combination of WIs for lower i's, and the WIs for lower i's, we can invert all of these and express them as a linear combination of UIs for I smaller than P. So we get this kind of a formula. And again, when we open this up, each one of these UIs is going to meet one of the UIs over here and become 0. So this becomes U1 wedge, etc. U P minus 1 wedge WP. And we can repeat the process with the remaining term, and we get this. So putting all of this together, we got that the product of the WI, the wedge of the WI's norm is this product, which is the co-volume that we want. Okay? Questions about this corollary? So this corollary was why we started this whole business. It's just showing us that this exterior algebra formalism can compute volumes for us. Let's state some corollaries that we're going to need using this formalism. Hopefully I'll have time to prove it today, and if not, I'll prove the remaining stuff tomorrow. So the first thing we need, suppose L1 and L2 are both primitive additive subgroups of a lattice L. And let's let V1 be the span of L1. Let's let pi from Rn be the projection on the orthogonal complement of V1. Then pi of L2 is discrete in V1 perp, and the co-volume of pi of L2 times the co-volume of L1 is the co-volume of L2. So I'm giving you a way to compute the co-volume of a lattice. So we suppose we want to compute the co-volume of L2, and we already know the co-volume of L1, and L1 is contained in L2, and everything is primitive. Then this is the formula that we have to use. We project L2 modulo L1 onto the orthogonal complement and compute the product. So proof. We start with a basis for L1. And since, so we can compute L1 to the basis of L2. That's denoted by U1 up to US, and then VS plus 1 to VI. By the previous corollary, the norm of the exterior power of the UIs is the co-volume of L1. And if we compute if we write down this projection of V, for every V, pi of V is just V where you subtract off a vector UV, where UV is in V1. V1 is the span of L1. that just follows from the definition of the orthogonal projection. You're projecting V onto the perp means you're subtracting the unique element of this space such that this guy is orthogonal to this guy. So the co-volume of L2 is this thing by the previous corollary, and this is let me just write it down again. This is Vs plus 1. I'm using this, so this is pi of Vs plus 1 plus u of Vs plus 1, and so on for each. I just plugged this expression into here. And by the same argument that I gave you before, all of these terms, when the brackets are opened up, when the zero power expression is opened up, they're going to meet elements in the same in space that contains them, and they're going to give us zeros. So this becomes this expression, and then because of the orthogonality, another statement that we just proved, we can open this up again as a product of and this is the volume of L1 times the volume pi of L2. I guess I said something and didn't prove it. I said this, and I didn't prove it. I'll let you think about this. We already had an argument exactly for this in the previous lecture. I'll leave that to you as an exercise. Let me just mark that. So this is an exercise. Let me state another result which we're going to use. I don't know if I'm going to have time to give the proof. Maybe I will. So suppose we have. So here's another proposition. So suppose I have two additive groups. The lattice. And I denote by L1 plus L2 the group generated by L1, L2, i.e. L1 plus L2 is all the sums. And the proposition says that so if proposition, well, let's give this another. Let's write down another formula for this. That if L1 is the span over Z, and U1 up to US, and L2 is the span over Z. V1 to VR, then L1 plus L2 is the span over Z of the combined collection. I'm not claiming that this is a basis because there could be linear dependencies, but it's clear that this definition and this definition coincide. We can easily show the inclusion in both directions. So this is another way of writing down the definition of L1 plus L2. And here's the proposition. Suppose L1 and L2 are primitive. Then you have the following inequality. The covolume of L1 plus L2 multiplied by the covolume of L1 times L2 is less than the covolume of L1 times the covolume of L2. So this is going to be a very helpful inequality. I think I don't have time to prove it, so let me prove this. This is going to be crucial next week. And so let's prove this. Let's first do this computation in the case that L1 and L2 only intersect at 0. Suppose first that L1 intersects L2 is 0. And let's use the previous notation. In other words, L1 is generated by V1 to Vs, V1 is generated by, L2 is generated by V1 up to Vr. And so I'm claiming that U1 up to Us all the way up to V1 up to Vr are linearly independent. Okay. And here's the proof, because if you can get 0 as a linear combination, then you can split this up, linear combination up as follows. So you get that the sum AIUI is minus the sum BJ. And so this element belongs to L1 intersect L2. I'm doing exactly what you would expect me to be doing if I was working with vector spaces. I'm only doing operations inside these additive subgroups, but I still get this identity which lives in the intersection of the two additive subgroups. So this is 0, and so because the intersection is 0. And since the UIs are linearly independent, and since the VJs are linearly independent, we get this. So this proves the claim. So now I can apply the previous corollary about using the wedge product. So what I want to have on the left-hand side is this. Right, remember that L1 intersect L2 is the 0, the trivial space, and we had a convention that the covolume of the trivial space is 1. So this is just that. And by the previous proposition, this is the norm of the exterior power. Which is so now we got the proposition in this special case where the intersection is trivial. If we're in a general case, Yeah, so I'm gonna prove the statement modulo a claim, and then I'll just write down. I owe you something from a inequality at the beginning of the lecture, and there's a claim that I'm going to state and give you the proof and put it on the lecture notes, so it's not worth spending time over. So let's just state the claim. In the general case, the claim is there is a primitive R tuple W1 up to WR such that span over Z W1 up to WR is L1 intersect L2, and this is also primitive in each one of the LIs individually. Okay, so this is a claim that I will post the proof of, and let's just conclude the proof using the claim. So by the claim, assuming the claim, W1 up to WR is primitive in both L1 and L2, and I can complete it to a basis, so can find UI prime and Vj prime such that L1 is the span over Z of W1 up to WR V1 prime V prime S prime. L2 is span over Z W1 WR V1 prime V I prime. And now I'm going to apply the previous, so L1 plus L2 is the span over Z, W1, WR, V1 prime, V prime S prime, V prime R prime, and I can apply the previous claim with previous corollary with L0 equals L1 intersect L2. Pi is the orthogonal projection from RA to the perp of the span of L0. And if you work out what this is saying, you see that the co-volume, this gives the co-volume of Li being the co-volume of the projection of Li times the co-volume of L0 for I equals 1 and 2, and similarly the co-volume of L1 plus L2 is the co-volume of pi of L1 plus L2 times the co-volume of L0. And let me call what I want to prove star. I already called it star. So basically what you get is from the previous case, from the case we already did, the co-volume of pi of L1 plus L2 is less than or equal to the co-volume of pi of L1 times the co-volume of pi of L2. And now multiplying both sides by the full volume of A squared, we get stuff. So I'm sorry this was kind of fast, but I didn't want to spend time on it next time. So I'll distribute the notes with some extra information, and you'll see the complete proof. Okay, are there any questions? All right, so see everybody again in a week's time.